Hello again, this is Cal with sections 3.5, the Cauchy criterion, and section 3.6, which I think is called proper divergence. We'll get there. Alright, so section 3.5 is about maybe the most important remaining definition in the chapter, which is called Cauchy sequence. You absolutely want to know definition 351. This is pretty important, and the examples are pretty important too. So read that stuff carefully. Again, the book doesn't do a great job of providing pictures here, and we'll do that in class, but it might be worth your time to try to draw a picture of what a Cauchy sequence should look like. It basically says that once you get, if you have an epsilon in mind, if you have a distance in mind, then once you get far enough out in the sequence, all of the terms that are at least that far out are within that distance of each other. Once you get to a tail of a sequence, the entire sequence lives within an epsilon neighborhood for any given epsilon. Anyway, that's what Cauchy sequence is. The next couple lemmas, 353 and 354, are used in the proof of 355. They're important, but the Cauchy convergence criterion 355 is more important. So, read these once and then move on to the main thing down at the bottom of 86, which is the Cauchy convergence criterion. This is real money. This says that for a given sequence, being convergent and being Cauchy are the same thing. One implies the other, and vice versa. And sometimes it's easier to show directly that a sequence is convergent. Sometimes it's easier to show directly that a sequence is Cauchy. This is pretty important. Do read the proofs of those two lemmas and of the Cauchy convergence criterion. And then there are examples in 356 of sometimes when it's easier to show that a sequence is Cauchy instead of directly convergent. I also like the ending of 356a, where it shows how we can prove what the limit of this sequence might be. And it even goes through, at the bottom of 87, something that we try that doesn't work, which is kind of interesting. In particular, we can kind of see that Cauchy sequences are often useful when you have a recursive sequence. Same with monotone sequences. Anyway, all of these examples are pretty good, and I recommend that you read them carefully. Starting at the bottom of page 88, we get into this discussion of a notion called contractive sequences. This is more or less a side thing. It can sometimes be easier to show something as Cauchy by showing that it is contractive, but I wouldn't call this a central part of the course, the way that Cauchy sequences are. Still, the definition 357, the theorem that every contractive sequence is Cauchy, is important. The proof might be a little hard to follow. I still recommend that you try to read it. And the example here, 359, is really nice, about ratios of Fibonacci sequences, which is actually kind of great. And I don't know that corollary 3510 is too terribly important. I think we can kind of leave that aside, as well as the following example. So that covers section 3.5. Then we get into 3.6, properly divergent sequences, which talks about what it means for a sequence to go to infinity or to negative infinity. The definition here is pretty important, and you do definitely need to know this definition, 361, of what it means when we say that a function tends to, a sequence rather, tends to infinity or negative infinity. And then we have examples in 362. We have a theorem about how to tell when a monotone sequence is properly divergent. I think it's a pretty obvious theorem. And then we have another theorem about comparing properly divergent sequences. Again, this one should be relatively obvious. And finally, we have a kind of ratio test for properly divergent sequences, which also can be useful. Not as useful as the previous two, maybe, but still useful. And that kind of ties together this section, and not a terribly hard section, 3.6. So that's all I have for today.